It is a pleasure to welcome you to the third edition of the lecture series on advancements in geotechnical engineering, from research to practice. The AGERP lecture series is a pro bono initiative led by Dr. Partha Mishra and Professor Sarat Das. Initiated in 2020, it is aimed at disseminating the coupled learnings from academia and industry on some of the key topics in geotechnical engineering. The International Workshop on Unsaturated Soils was hosted in 2022 during the third edition of the AGERP lecture series. The following lecture on swelling and shrinkage of a compacted expansive soil, a microstructural insight, was delivered by Professor Olivier Buzzi at this workshop. Dr. Olivier Buzzi graduated from the École Normale Supérieure d'Éducation, one of the most prestigious public institutions of higher education and research in France. After obtaining his aggregation of civil engineering in 2000, he completed a master on rock joints and PhD on the hydromechanical behavior of contacts between geomaterials in the context of nuclear waste storage at the University Joseph Fourier, Grenoble. Moving to Australia in 2005 to take up a postdoctoral position was the first step in Olivier's career at the University of Newcastle. He began lecturing at the university in 2007, became a senior lecturer in 2009, an associate professor in 2012 and a professor in 2018. Olivier's research interests span from rock mechanics to soil mechanics, with a long history of successful industry collaboration and a taste for challenging problems such as dynamic fragmentation of rocks and mining geotechnics. Olivier combines experimental, theoretical and numerical approaches to conduct his research. Olivier served as an editorial board member of Computers and Geotechnics. He was an associate editor of the Canadian Geotechnical Journal and is a current associate editor of Rock Mechanics and Rock Engineering.
Evening, morning, afternoon to everyone out there. So as Partha said, my name is Olivier Buzzi. I'm with the University of Newcastle, and I will talk today about swelling and shrinkage of compacted expansive soil with a perspective on microstructure. I'd like to acknowledge my collaborators on this work, Dr. Shangyang Yuan and Professor Xingfang Liu, who are both at Southwest Jiaotong University in China. I'd like also to thank the organizers for this invitation, and it's a pleasure to be here today with you to share this research. So the talk is about expansive soil, and those soils are basically characterized by the fact that they contain smectite, and smectite is known to be a swelling mineral. So it has the ability to absorb a lot of water in between the platelets, the clay platelets, and that for two reasons. The platelet surfaces is negatively charged, so it attracts the positively charged water dipoles, and there is a weak bonding between the platelets that actually allows the platelets to be pushed apart, take up the moisture, the water. And as a result of this phenomenon, what happens is that those sort of soils experience large volume changes if you wet them or dry them. And as you can imagine, that can pose some problems for structures that are built on expansive soil or using expansive soils. And you've got such an example here on this photo. This is a building in Newcastle that has been vacated and cannot be used anymore. It's got very serious structural damage, which is caused by those movements, and in particular differential movements of the expansive soils it's built on. Now, one of the issues we're dealing with is that those soils are fairly common in Australia. You've got a map here that was produced in 1983 by Richards, and it shows in black the extent of expansive soil. And one of the problems is that those areas actually coincide a fair bit with areas where we have a lot of urban developments, infrastructure developments. So basically that poses a problem, geotechnical problem for engineers. So we've got thousands of dwellings built on reactive soils, but not only that, it's not only a matter of simple residential houses. We've got big projects as well involving expansive soil. So you've got, for example, here a photo of the Torrens to Torrens project in Adelaide. So it's a major infrastructure work, and there are some expansive soils involved in here. You've got now a photo of the cutting of the Hunter Expressway, which is a highway near Newcastle. And that cutting shows you interbedded layers of weathered claystone, expansive, and coal material. And for financial and environmental reasons, those materials were actually incorporated in the earthworks of the freeway, so posing challenges. And one of the latest development here in New South Wales, the international airport, the new Sydney International Airport, is built on a profile that has a lot of Bringelly shale, which is known to contain expensive minerals as well. So it is a real engineering problem to deal with those expansive soils. And as such, it's quite important to be able to characterize the volume change upon wetting and drying of those soils. So there's volume change upon mechanical action, and there's the volume change due to wetting and drying. Here I'll be focusing on the wetting and drying side of it. So we're looking at, in particular, at shrinkage curve and the swelling response. And the swelling response is in strain and pressure. And we'll see it may involve some collapse, which I'll define and explain. Now, just a quick note, you've had talks about desiccation cracking. I just want to say it is out of the scope of this presentation. It is relevant for engineering practice, but out of the scope of this presentation at the time being. So the idea here for me was not to give an extensive lecture on the topic, but just use this as an opportunity to share some of our findings on those matters there, and try to actually look at the microstructural aspect of it to explain, interpret some of our results here. And the reason for that is because we know from the 50s that there is a very strong influence of soil structure on the soil behavior. It's been recognized fairly early for compaction tests, for example. That's one classical example, but you'll find other examples of that. Now here we talk specifically about microstructure because we're looking at what's happening at a level that we can't see with the naked eye. So we're not talking about those sort of cracks. We're trying to understand what's happening inside the soil at a level that we can't see. So how do we actually characterize the microstructure? If you go back to the early literature, what you find is that description of microstructure is typically qualitative. You've got those drawings of rectangles showing the platelets or arrangement of assemblies of platelets with the edge-to-edge, edge-to-face, face-to-face contacts. Sometimes you've got scanning electron microscope, or SEM for short, images supporting the analysis. Now, these days, you've got a range of quantitative options. If you're interested in characterizing in a quantitative manner the microstructure, you've got nitrogen adsorption, MIP, which is mercury intrusion porosimetry, tomography, and others. So we've used for all our research the MIP technique, mercury intrusion porosimetry. It gives you a quantitative analysis, but you got to be careful. It's not a what I call the magic bullet. It relies on assumptions. It's got limitations. So you need to be aware of those when you use such technique. And we typically combine SEM analysis and MIP to get a more comprehensive assessment here. So before going further, let's have a quick look at what we get from an MIP analysis. So those aren't quite the raw data. They've already been a bit processed, but they're the typical sort of curves you get. So in the top part, you've got what we call the intrusion curve, and that's the evolution of what we call the intruded mercury void ratio, or EMIP for short. And what this is defined is basically we're looking at the volume of mercury that has been intruded in a specimen over the volume of the specimen. So the specimen has no water in the mercury, it's only solid particles, so that's the VS. And this is a function of entrance pore diameter. So that's the thing you want when you characterize microstructure. You want to know about pore size. So the intrusion curve starts with a large diameter, easier to intrude, and we push the mercury in and progressively intrudes the smaller pores. Now, if you take this curve and you differentiate it, what you get, you look at the gradient and you plot the gradient as a function of entrance pore diameter, you get the pore density curve, which is the one below there. And we like this one because it shows clearly peaks. When you've got a moment where there's a lot of intrusion, that is a lot of volume mercury going into a certain pore size, you've got these peaks forming in the density curve. So here you've got a typical bimodal distribution with a very large peak pronounced for a range of pore size in the order of 10 micron, and a smaller peak in the order of between 10 to -2, 10 to the -1 micron here. And when we look at this, we typically like to call that macropores and micropores. And you've got an SEM picture here showing what actually showing a clay aggregate, and the macropores would be the space in between the clay aggregates, and the micropores is basically what's happening inside the aggregate here. So that's the way we tend to analyze the results here. Now, why do we do this? Sorry, and one of the advantage of the MIP here is that the range of pore size you get is fairly wide. It goes from 6 nanometers for our model, at least. The higher the pressure of the system, the lower will be the pore size for 6 nanometers, all the way to 400 microns, so 0.4 of a millimeter. So fairly wide range. Now, what happens is that soil structure changes when you load the soil hydromechanically, so external stress or hydric stress, and it's even more pronounced for expansive soil. And I wanted to show you the results of Maryland clay, which is our favorite candidate soil here in Newcastle. It contains about 10% of interlayered illite and smectite. It's got a plasticity index of 46%. And starting by the figure in the middle, so these are all pore size density functions, so showing the peaks of pore families, and you've got pore diameter on the horizontal axis. Starting with the one in the middle, what you see is that we've got here conducted an MIP analysis post-compaction. And as you reduce the void ratio of the specimen, so the more you compact it, the more the macropore family reduces. So the micropores are unaffected, but the macropores they reduce in density and in size. Now, if you take such a compacted soil and you allow it to swell freely without surcharge, the pore size distribution may go from the continuous black line to the blue line. And if you did MIPs along the way, if you stopped the test and you did MIPs, which we did, what you see is that you tend to have the two pore families sort of merging. So that big pore family in the middle is partly the result of the merging of the two families of pores there, with a reminiscence of micropores on the left. And basically, if you take an SEM photo, what you find is you go from a clearly aggregated structure to something like a matrix-like, where you can't really see macropores and micropores anymore, which is consistent with this sort of distribution. Now, if you look at air drying, starting from the blue line, you find that this time the drying affects both micropores and macropores significantly. So the micropores tend to reduce, that's your aggregate shrinking, and the macropores can reduce or increase because you may have opening of porosity in the process. It's quite a complex phenomenon, that one. So if we consider the fact that microstructure affects soil behavior, and if you see that microstructure changes so much during the hydromechanical loading processes, it makes sense to try to follow what's happening with the structure, and in particular, try to quantify it. So one thing is to show it and to have here something qualitative, but the question is, okay, how do we process those curves here to get some quantitative information that we can use? And the way we do this is to define a void ratio for the micropores, so that's E lowercase m, and a void ratio for the macropores, E uppercase m. And how do we define those from those curve here, those results? We typically, we use the intrusion curve here. It's got void ratio in the vertical axis. So we use this to define those two void ratios here. But what we need is we need a boundary. We need a boundary that says, okay, all pores larger than that value, that boundary, are macropores, and all the other pores are micropores. So we need to set a boundary here. Once you've set the boundary, you can basically look at how much mercury has been intruded for the larger pores and say, well, all that mercury here, that goes into the macropores, and you can read off the axis the macro, E macro, and the rest is basically E micro. So the rest being the void ratio of your specimen as you've prepared it, or as it is, as it stands, minus the void ratio of the macropores. Now, these whole results here, those values you're going to compute depend heavily on this boundary you select in here. And there's many criteria in the literature to select a boundary. There's no good or bad criteria. They're different criteria based on physics. or logic. And the thing is, you got to be a bit careful. You got to assess the sensitivity of your results to the choice of your boundary here, because it may affect those two values of void ratio a fair bit. So you got to be a bit critical about it. If you want to know a bit more about this, there's a publication by a PhD student, Yuan et al. 2020. I'll give you a list of publication at the end where we've discussed those different boundaries and what the implications are when you pick one or another. All right, so with this presented, let's delve into some of the results here. So the first thing I wanted to talk about is the shrinkage curve. And shrinkage curve is the evolution of the void ratio of a soil as it dries, and we correlate the void ratio with the amount of water. And that can be in terms of gravimetric moisture content, W, volumetric, theta, or even the water ratio, EW. So you've got here a typical sort of shrinkage curve where the void ratio follows the 1-to-1 line, meaning we've got saturation. And the gradient of the line is the GS of the soil. You've got an SEM photo of the soil here. That's a remolded specimen. So the SEM is taken at a void ratio of 1. So the soil shrinks, but doesn't desaturate, follows the 1-to-1 line, and eventually after a while, they pass from the line and you get into the residual stage where you've got the shrinkage limit. So that's well known. Now, what's interesting is that if you now test an intact bed of marine clay, you've got a different result. So similar sort of trend, the soil first shrinks along the 1-to-1 line, but desaturates much quicker. And the value of final void ratio here and the value of shrinkage limit aren't quite the same. And what that shows is that basically you've got a strong influence here of soil structure. We've got larger pores in the intact soil, which basically means we'll have a quicker desaturation. So the blue dots depart from the 1-to-1 line much quicker, and the volume change is not as pronounced as the one of the remolded soil here. So this is an effect of structure. And when it comes to geotech engineering projects, depending on what structure the soil will have in your project, well, you may need to test the soil intact or remolded or compacted. So for example, we've got projects where we dig the soil out and recompact it in an embankment. Other projects, say for example, you've got a soldier pile wall where you install the piles in an existing profile of soil and you don't dig or backfill, the soil at the back of the wall will be in its intact or close to intact condition. So you need to be mindful here when we try to characterize the volume change, to try to do that on a soil that has got a structure as close as possible to what we're going to have for a project. Now, I don't know how many of you have tried to or have measured shrinkage curve on a regular basis, but here we've managed to get a lot of point and a very nice tracking of the volume change here. And we did that using a technique that we've developed because we got a bit frustrated with some of the techniques that were typically used. And I'd like to present that to you because it may be quite useful. In particular, the typical way to do it, or probably the most logical way to do it, would be to have a specimen of known shape, clearly defined shape, typically a disc, and you measure the dimension of the specimen. And as it dries, you keep measuring the dimension, you know the volume, you know the mass, you can plot the shrinkage curve. The issue comes where you've got irregular shapes, or if you've got warping or distortion upon drying. An irregular shape could be basically if you've got some intact soils, sometimes they don't really have, you can't really cut them into a nice shape because crumbs come off and so on. So in that case, the fallback position is the immersion method, the buoyancy technique, where you immerse the object in a mass, you measure the apparent weight, and from the density of the fluid, you can work back the volume. Now, the question is, what fluid should we use for that? And the one that is really good because it's non-wetting is mercury. But the issue with mercury is safety. Plenty of safety issues around mercury, so quite difficult to work with mercury in an open container these days. Water is a fluid, but it's absorbed by the specimen, so it doesn't quite work. Well, you can use oil, but oil, it's not absorbed by the clay, but it contaminates your specimen. So if you've got cracks, big pores, it gets into there, and basically you end up having inaccurate readings. So what people did or suggest is to basically coat the specimen. And one known technique is to use paraffin. So you've got a photo here, which I found from the web of a paraffin-coated specimen. The issue with this is that if you want to do a whole shrinkage curve, you got to have basically plenty of specimens in parallel, or you got to have to coat, remove the coating, new coating, remove the coating, and so on, and all with all the accumulated error that you get on your measurement. There's also another technique that was developed called the plastic bag technique, where you put a specimen in a plastic bag, vacuum it, and then immerse the plastic bag in the liquid. That has got other issues as well. I mean, vacuum is a stress. You're putting some stress on the specimen. You've got the vacuum bag, the bag which is linked to a tube as you immerse it. And there's a lot of handling and smearing of specimen. So we thought, well, surely we can do better here. And what we propose to use is a medical product. That's a photo of a hand spray plaster. There's a range of companies making this product. And it's basically designed to be sprayed on wounds so that the wound can breathe, but wouldn't get wet if you have a shower or go for a swim. So it's waterproof, breathable, stretchable, non-toxic, and relatively cheap. And what that does is that if you coat the specimen with this, you can have moisture exchange, gaining or losing water by vapor transfer, but you can then take the specimen, immerse it in oil or water for a short period, and the spray, the plaster will act as a barrier, so your specimen doesn't get contaminated. So what you do is take the specimen, put it on 3 prongs here, spray the top part of it, cover it so that it doesn't dry too much. After a while, turn the specimen upside down, repeat the operation so it's entirely sprayed. Then you can expose to drying if you're after the shrinkage curve, or humidity in a fog room if you want a swelling curve. And then basically use the buoyancy technique, immersion, to get the volume of that specimen here. And that works for any irregular shape. So we compared the results of that technique to plastic bag method and the wax method. You've got here the results of the two in gray dots and black crosses. And you've got a lot of scattering. We didn't do it on purpose to show how well aligned the blue diamonds were. That's just a result of the manipulation here. So it was a lot better. And the benefit of this is that it's also fairly useful if you want to measure retention curves. If you want a retention curve expressed in saturation degree, you need volume. You need a relationship between volume and moisture content, or volume and saturation and suction. Well, that technique allows you to get really nice tracking and accurate data here. So it's pretty useful. Now, let's move on to the swelling response here. And just as a preamble, I want to say that all I'm going to present here is only in 1D. Now, 3D swelling in all directions is relevant for engineering practice. It's more complicated. So I thought, let's start with 1D information there and see how we can move from there. So our experience here in Newcastle is that when we have to deal with reactive soils, there's a range of parameters that engineers like to measure, atomic limits, linear shrinkage, and so on. And when it comes to the swelling response as such, they're often interested only in the free swell strain. So that's take the specimen in an odometer test, let it swell in 1D under full saturation without total stress applied to the specimen. So maximum swelling strain you're going to get. And the swelling pressure. So again, full saturation, swelling to full saturation, no volume change allowed, and get those two numbers. And from that, assess how reactive the material is. So you can actually, on a stress strain plane, you can plot those two results. You've got here swelling pressure on the left axis. So that's the maximum stress to when you've got 0 strain allowed. And the free swell strain is here at the maximum strain under no stress applied. So before we keep going, I'd just like to clarify the conventions here for my presentation. I will be talking about strain rather than void ratio. So it's a bit against the geomechanics conventions, simply because when you compare the amount of swelling for two soils at different void ratio, the void ratio can be a bit tricky to interpret the swelling. Whereas if you look in terms of strain, you get a clear idea of the magnitude of swelling you're observing. I'll consider that positive strains or positive displacement correspond to swelling because the focus is on swelling. So otherwise I'll have this negative sign all along. And the stress on the y-axis here, it's a total stress because swelling, the way we measure swelling pressure is with a load cell external to the specimen. So technically we measure total stress. And when you put a load on a specimen, it's a total stress you apply to the specimen. So at this stage, stress here, consider that as a total stress, but it can be either the swelling pressure measured or a total stress applied to a specimen. Right, so we've got, with that clarified, let's move on. We've got those 2 points here, which are often requested for projects. But what we know is that if you allow a little bit of deformation and then you block the volume, the soil will exert some pressure, and the magnitude of that pressure drops as more and more deformation is allowed. And that's represented here by this red curve here. Now, what we know as well is that for a given soil and boundary condition, the swelling response is a function of the initial suction, the initial void ratio, and the suction change. In other words, the magnitude of hydration. So in fact, you don't have one curve, you've got many curves, and that curve shifts upward as the amount of hydration goes up, the initial suction goes up, or the void ratio, initial void ratio goes down. So the denser and the drier your specimen, the more swelling you're going to get. Now, the change in suction is quite interesting because what we've observed, or what people have reported, is that most of the swelling occurs at very low values of suction. So what we've got here is data from Escario et al. In 73, replotted. They took a specimen at an initial suction of 1800 kilopascal and weighted it in 1D swelling under stress and reduced the suction incrementally and measured the swelling strain. So you've got swelling strain in vertical axis, suction change on horizontal axis, and the dashed line here is full saturation. Now, what you observe is that most of the swelling, this is a nonlinear response, and it's towards the end of the swelling process, of the wetting process, that you've got most of the suction, the swelling strain. At the beginning, not a lot of strain, even though the specimen is being wetted. Now, how is this relevant? Well, in the lab, we tend to often do test to full saturation because that's quite practical. But in the field, you got to ask yourself, to what extent will a soil undergo full saturation? Or do we have partial swelling, partial hydration of the soil under a given environmental condition? So again, this is possibly, the full saturation swelling would be the worst case scenario, but is it the most common case? Maybe not. So from the literature, we know clearly what's the effect of vertical stress on swelling or confinement. We know what the effect of suction chain is. One thing that we don't quite know is what's the effect of the boundary conditions, right? We've been talking about free swell and constant volume. So we know what these two do. What happens in between? Does it matter? So what we looked at is establishing in the first place this swelling response. So how the combination of swelling strain and swelling pressure evolve as you allow for more and more swelling strain. And we did that on compacted marine clay using a constant volume test that gives you the swelling pressure in B. One free swell test gives you the free swell in A, and a range of swells under constant stiffness. And those are basically soil swelling under a spring. So you've got a linear relationship between pressure and of stress and strain. And then what we did, so with those tests are shown here by the blue arrows. And then what we did is we did, okay, right, let's now conduct other tests using different stress volume paths and see where the final stress and strain is, and does it fall close to this swelling line or not. So to do that, we did a series of tests under constant vertical stress, that's the horizontal red arrow, and what we call mixed boundary conditions. So swelling at a certain stiffness, and then block the volume, and let the swelling pressure develop. See what happens. And at the end of all those tests, let's conduct some microstructural measurements using the MIP technique and see what happens inside the specimen. So the first series of tests we did was with the Hunter Expressway claystone, the one I showed you a photo of in the first place, and it contains 27% of mormarionite, which is a sort of smectite. And we consider 2 initial water contents and 2 initial void ratios. So that's 4 combinations of starting condition. And the first thing you see, so in stress versus strain planes, you've got the different responses established using the specific tests. What you see is, first, the denser the specimen, the more swelling we get. That's how the empty diamonds sit above the full circles for both cases. So that's consistent with what we know, and that's good. Now, if you look at the effect of moisture content, you'll find that for a given void ratio, say 0.48, the wetter the specimen, the less swelling you get. So for example, if you look at a swelling strain of 5%, you'll find that you've got more swelling pressure developing in the drier specimen. So that's reassuring that, first of all, you establish those curves and they follow basically what you would expect here. Now, the question is, what do we get if you superimpose the results of the mixed boundary conditions and other tests? Well, that's what you've got in black in here. And what you see is that regardless of the path, you basically end up fairly close to all the other points in here, or in between where you would expect to find that line here. So at the macroscopic scale, we end up with an expression of swelling in terms of strain and stress or swelling pressure, fairly similar to what you'd find along the line here, the swelling response we've established with the prior test. Now, what happens in terms of microstructure? If we take those 2 black dots, the diamond and the inverted triangle, and we compare the microstructure, these 2 are the black lines in here. So the continuous black and the dashed black. Just to give you an idea of the variability of structure, the purple line is as compacted, the green line is free swell, and the dashed line is swelling under constant volume here. So you see there's a fair bit of change in microstructure between the 2. And what we found is the microstructure of those 2 materials, having swelled along different paths, are fairly similar. So that corroborates the observation at macro scale here. Now, we did a series on marine clay as well, and these are only partial results. There's more results in a paper we published last year. And again, we basically observed the same thing. So we've got a swelling response established with a blue cross. Then you've got a series of other tests, constant vertical stress, the red lines, and mixed boundary conditions. And you find again that basically the tests, regardless of the path, basically end up in very similar to, very close to the swelling line here. And if you do some microstructural analysis, again, you find that the distribution of pores is fairly similar. There's a slight offset in that one at the bottom, point B, due to a gully here that we didn't quite explain, but overall the shape is very similar. The frequency of pores is very similar. There's just this slight offset here. So that sort of suggests that effectively you basically end up in the same spot, regardless of the path here. Now, why is that? How do we explain this? And to explain that, we had to go back to some microstructural analysis. And what I'm giving you here is our interpretation of this. If somebody has got a different idea, I'm be glad to hear it. But what we did here was we conducted a series of tests. There was another series of tests, swelling under constant vertical stress with increasing value of stress. And at the end of it, again, microstructural measurements. And what you see is that the level of confinement you've got on the soil has this huge effect on the microstructure, right? So that's for everything to saturation. If you stop, the specimen doesn't go all the way to saturation and stops in between, the microstructure will be different. So clearly, the stress here is a key driver of what the microstructure of the soil will be here. So our interpretation of that in the context of the previous test is that basically what matters when it comes to the swelling response and the path followed to get to full swelling is that it's the magnitude of the maximum applied stress that matters more than the path itself. So as long as you end up with the same maximum stress, the strain you're going to get and the microstructure you're going to get will be similar. If there's more swelling and then coming back, so if you reduce the, if you overtake the swelling line and come back, might be a different story, as some of the test results on swelling pressure you see in the literature tend to suggest. So the relevance of this is for engineering practice is you've got in practice very often you don't have a constant volume or free swell condition. You've got something else. So the soil will swell in a way that you've got a combination of strain and pressure. But you can estimate that from the swelling response as long as you've got an idea of how much stress will be applied to the specimen in the end. Now, I'd like to go back to this picture here and focus here on this point C here. And what we've got here is we basically have zero strain for an applied total stress of about 400 kilopascal. And if we increase that stress, what we're going to have is a negative strain. So the soil will be basically compressed and we'll have compression instead of swelling here. And that leads me to the concept of wetting-induced collapse. That's something that is known since the 60s. And it's a reduction of soil volume or swelling pressure upon wetting under load. So you take an unsaturated specimen, put a load onto it, wet it, and you've got either swelling, increase in swelling pressure, and then reduction. That's when you do a test at constant volume. Or if you do a test at constant stress, like the blue line, where you've got the displacement measured on the right axis, going down is specimen height reducing. And what you've got here is at point A, this is all 1D, an odometer. Point A, you apply the load. So the specimen is compressed to B. Then at B, you wet the specimen and you have initially some wetting. And then basically you've got a collapse. Specimen height reduces. Now, this is how the expressions here of collapse. Now, how is this relevant to practice? Well, you've got some soils that are naturally collapsible, and loess is one. There's plenty of loess in China, and you've got a photo here of areas where the soil has collapsed. So you can imagine if you're building on soil profile like this, may be challenging. It also affects earthworks. So there tends to be a belief that if you've got a compacted earthworks, collapse is not a problem. It's not a problem if it's done well, but it's not always the case. And you've got here a photo, for example, of a bridge abutment where the embankment here has collapsed after heavy rainfalls, and that brown mark basically shows the magnitude of collapse here of that soil, so fairly significant. In Australia, we've got a different challenge with collapse. What you see here is a waste rock dump coming from open pit mining. So it's a consequence of mining that we create these mountains of dirt. And those are placed without much compaction. It's basically compacted by self-weight. There's not a lot of compaction activity happening when this material is placed here. And these are hills of hundreds of meters in height. And at the end of the mining operation, where the mine reaches its end of life, this is all capped and turned into vegetated ground. Now, what happens is because there's kilometer squares and kilometer squares of it, the question now arises as to what extent this ground is suitable for development. And you can imagine if you've got something here that hasn't been quite compacted, and it's not saturated, and we wet it, and there's a lot of load on it because it's really high, there could be a lot of collapse here happening. So that's an area where in the mining geotechnique space where collapse is very relevant. Now, How do we actually capture collapse or explain collapse? There's different models to do that. And I'll just present some of the results here in the typical two-stress, with a two-stress approach, where you've got suction and net stress. So what happens is, for the test we conducted in the lab, we start with a loose packing of clay particles at a certain moisture content, and that's at point A. And then we compact them to a certain level, point B, offload them and bring them back to a certain stress, point C, to do a test, a swelling test in the lab under constant vertical stress. Now at point C, here, we're gonna wet the specimen, and in the suction net stress plane, you've got what we call the LC curve, loading collapse curve, and that is basically the yield point that tells us if we're gonna have collapse or not. If the stress path crosses that line, you've got collapse according to the model. So, the way to look at those curves is that for a given void ratio, this LC curve is the locus of compaction stress and suction point. Right? So at a certain point here, it's how much stress was needed to get to that void ratio, or maximum stress applied, and what is the corresponding suction. Then when you, at point C, and you wet the specimen at constant vertical stress, so LNP doesn't change, you go down, suction reduces, you cross that line, you've got collapse. And you can work out the magnitude of collapse from the relative position of the compression lines here, the one for the saturated soil and the ones for the unsaturated soil. So that's one framework in which we explain collapse. Now, what's really important here is to remember that the LC curve is defined at constant volume, or for a given void ratio. So in other words, if I want to test a specimen here compacted at a higher void ratio, I'll have to consider the blue LC curve compared to the black one, because it takes less stress to achieve a higher void ratio. In contrast, if I want a lower void ratio, yeah, I'm going to have to compact more. So that basically means it shifts the curve to the right here. So before we move on to presenting some more results here, just wanted to explain a little bit how we can measure the LC curve from the compaction here. So if you do a series of quasi-static compaction, not the dynamic ones, you can, to a target void ratio, you can measure the total stress you apply to the soil and suction. If you've got the combination of void ratio, total stress, and suction, you can basically plot the LC curve. You've got to repeat that for a range of suction values, and you can build the whole curve. Now, when it comes to suction here, what's really helpful is those sort of results you find in the literature. This comes from Romero et al. In 1999, but you've got other plots. And what it shows is that in the standard Proctor plane, you've got, when the specimen is really dry, the suction lines profiles are vertical, and basically meaning suction doesn't depend on the dry density of the soil. But as you approach the optimum, or you exceed the optimum, then you tend to have a dependence of suction on the degree of compaction of your specimen. So how does that matter for our problem here? If you're on the dry side of the optimum, suction can be measured pre or after compaction, not a problem, it's independent of the dry density. But if you're close to optimum or on the wet side, you need to measure suction during compaction. And that's, for example, using a tensiometer. You've got here, for example, for Marion clay, the evolution of measured matrix suction with vertical stress during compaction. And what you see, optimum moisture content is 24%. If you're at 13%, we're dry, there's no change. If you approach the optimum, you start to have some influence here, and that's related to the concept of mechanical wetting. And if you exceed the optimum, you got a very large change of suction during the during compaction. So when you try to associate a value of suction to a value of stress to build the LC curve, you need to be mindful of what value you got here and make sure you measure suction. Okay, so with that explained, let's go to our experiments now. So what we did is we established the LC curve for different void ratios, and we decided to conduct a series of soil tests under constant vertical stress inside the elastic zone. So what I mean is basically away from the LC curve. This is a plan where you've got suction, or log of suction in vertical axis, log of net stress in the horizontal axis. The red dots is the measured LC curve with the different points where we conducted those quasi-static compactions. And we had planned to start with the dry specimen and wet it under different stresses. So something fairly common somehow. But what actually was a bit surprising here is that when we did those tests, what we observed is collapse in areas where we weren't supposed to observe collapse. So take C dash, double dash here, which is quite away from the LC curve, and that's a log scale, so it's quite away from the LC curve. And what we've got is collapse. The specimen reduces height as we wet it. And so we are quite surprised by that. And we had that in other places. And we thought, okay, right, there's what's going on here. In the end, we had swelling at B, but collapse at C and D. So first thing we did is we questioned the quality of our data. And we repeated the test and we got the same conclusions. So then we thought, okay, well, is it because we start with a void ratio of 0.8 before swelling? We have an LC curve at 0.8, but as the specimen swells, the void ratio increases. And we know that the LC curve is defined for a certain void ratio. If you've got a higher void ratio, the LC curve is on the left, right? And that's basically what's shown here theoretically with the blue line. So we try that, and basically that's not it. That wasn't the explanation, because the degree of swelling we had didn't really change the void ratio that much, and the LC curve was nowhere near where we needed to be. So we thought, okay, could it be the microstructure then? And if you think of it, collapse occurs in the micropores. You need to have an open porosity to observe collapse. And you can refer to the recent review by Lee et al. About this. We know reactive soils undergo significant microstructural changes during loading. And we know that the LC curves are established the way we did it, at least, and many people do it. We don't really consider microstructure. It's all about the values of total stress and suction during the test there. So is there something here? So to do that, what we did is we did a series of compaction tests, and that's all the black diamonds on this proctor plane, so plenty of them. And we did some microstructural analysis. So for every point, we measured suction, maximum net stress, and the macro void ratio. And we wanted to establish a contour of macro void ratio. So that's the surface I call SSEM for stress, suction, and macro void ratio. And basically try to interpret our results here in the light of this macro void ratio information. So what we did is we conducted, after establishing those contours here, we did 3 pairs of swelling tests, 6 tests, B to B prime, B to B dash, 1 test, at the end of which we get a microstructural information, and B double dash, and get microstructural information again. And repeat that for C and D. The way we conducted the test is reduce the suction incrementally using the osmotic method. And after each test, get the MIP done and compute the macro void ratio and try to use that as an interpretation of the results here. And in particular, the question is, do we cross somehow this surface as we have collapse? So you got to remember here in D dash, for example, we have no collapse, but in D double dash, we've got collapse. So in order to see whether we cross the surface, because this is a 3D thing, you need to look at a cross section. So if you take a cross section along D dash, D double dash, and you look at the evolution of macro void ratio versus suction, that's what you've got. That's in blue. It's basically the contour plot of the macro void ratio, and the crosses are the void ratio, the macro void ratio at point D, D dash, D double dash. So what you see here is, well, we didn't really cross that surface here. It didn't really work. And then we thought, but hang on, in D double dash, this is a macro void ratio post collapse. The specimen has collapsed here. So if we look at the magnitude of collapse, and we assume that basically most of the collapse occurs in the macropores, in other words, delta EM, the change in macro void ratio upon collapse, is the change in void ratio, you can plot a point D star here on the other side of the line here. So that would be the maximum amount of void ratio occurring in the macropores. But somehow it suggests that maybe, well, we have crossed that line. Now, if you look at C, we've got the same observation. And if you look at B, not quite. We've observed swelling. That point here is right on the surface. Have we crossed? Haven't we crossed? Not too sure. The thing is, there's a lot of uncertainty about those values because it depends on the boundary. The surface was established with interpolation between points, so it probably needs more data here to ascertain the phenomenon, but that's a lot closer than the loading collapse curve we had defined before, which is the conventional way to do it. So what those results suggest is that either we need to look at the loading collapse curve in terms of macroporosity rather than void ratio. The issue with that is you need to do 1,000 MIPs, and that's very costly and time consuming, so probably not a good way to do it. Or when we've got models for expansive soil, and there's not a lot of them out there. There are some. The coupling process here between the loading collapse curve and the stress pass during swelling probably need to explicitly account for this macro void ratio here to predict where the loading collapse curve should be. And in any case, again, it shows that we need to actually test soils with a structure that is relevant to the engineering problem we have to deal with, because microporosity or microstructure matters here again for collapse. So that concludes my presentation, and I'd like to present a few dot points here to summarize. So there's a lot of reactive soils in Australia, which pose a lot of problems, and there's a lot of reactive soils around the world as well. So there doesn't seem to be a lot of consensus on how we should treat them from a geotechnical practice perspective. On even research, there's a lot of interpretation. So there's a lot of work to be done here and a lot of relevance for practice. Now, one thing we saw or we suggested that you need to characterize the full swelling response, and that's the evolution of swelling pressure with swelling strain. And you can do that simply by a series of constant swelling tests under constant vertical stress. That's because basically we found that we suggest it's the magnitude of final applied stress that matters to define the strain you're going to get. And as such, the full swelling response can be applied to a range of other boundary conditions, right? Always keeping in mind the fact that we do this to bring knowledge for engineering practice. What are the boundary conditions in practice? It could be 1D, 3D, but also it's unlikely to be a constant volume condition or free swell condition. So being able to characterize the swelling in terms of strain and pressure for different boundary conditions is quite relevant. Now, what we found is that soil structure matters. Well, to some extent, it's not new. I mean, we knew from the beginning that soil structure matters, but the thing is, sometimes it's only qualitative. Now we've seen it fairly quantitatively to what extent it does matter. It was quite clear on the shrinkage curve, and it's going to affect other aspects of soil behavior as well. There's a retention curve, which you would have heard about in this workshop, collapse as well, we've seen. So if you're out there doing some swelling tests and wondering about loading collapse curve or establishing them from compaction data, keep in mind that the microstructure here could play a role, because it could explain some of the inconsistencies you've got between your loading collapse curve and the actual occurrence of collapse. It is possible there. So if you can, it is helpful to conduct microstructural investigation to try to interpret your results. We like MIPs because we've got one, or we have got one because we like it. It's convenient, but it's not perfect. So you've got to be aware about its limitations. And if you can't get microstructural information, at least try to test soils with a structure that is close enough to your engineering application, or try to minimize sample disturbance if you can. You've got here a range of papers that are presenting results on marine clay, which I've used for this talk, if you're interested. And with this, I'd like to thank you for your attention and leave you here with a video of a mercury intruded specimen of soil going through, having gone through microtomography to show where the mercury, how the mercury has intruded the pores. Thank you for your attention. Well, so you can conduct a PSD at any point in time, right? To the whatever hydromechanical loading to the soil you apply to the soil, you can stop and measure. The issue is that you have to remove loading. You can't conduct a mercury intrusion porosimetry on the loaded specimen. We've tried to freeze a specimen being loaded. You have to deal with very, very small specimen to do that. So going back one step here, to conduct an MIP analysis, you need to freeze dry your specimen, because the mercury enters the pores, and if the pores are filled with water, the mercury won't enter. So one thing you got to do is remove all the water. And if you remove the water by drying the specimen, you change the structure. So you got to freeze dry your specimen. Now, so the question is, to what extent, and that's one of the limitations, you got to remove the specimen, remove the loading from the specimen to be able to treat it. And then the question is, does the process of freeze drying change the structure as well? Now, if you accept that removing freeze drying doesn't modify the structure to a large extent, which some papers tend to suggest, and if you accept that you have to remove the loading, to look at wetting and drying, you basically need to take your specimen from a wet state, dry it, MIP it, or take it dry, wet it, and MIP it. Yes, it does. It's one of the limitations as well. But to some extent, if you've got the MIP technique should be used to get an idea of the relative evolution of microstructure rather than an absolute value of microstructure, right? It will not give you an absolute snapshot of what the microstructure is or information. It just doesn't work like this, because for a range of reasons, and the ink bottle effect effectively is one of those. So to those who don't know what the ink bottle effect is that a pore is not like a pipe of a constant diameter in which you push mercury. It's probably more likely to be like a bottle where you've got a neck and a body. And basically what happens is you got to push the mercury through the neck of the bottle first, and that's the pore diameter you measure. But then the mercury fills the body, and that's the volume you measure. Now, we've conducted recently that image I showed you at the end. We've actually conducted some image analysis on the mercury intruding the specimen to try to characterize the ink bottle effect, and it's not necessarily very pronounced. So if you take it as a relative information about relative change of microstructure, well, maybe there's not so much changes in the ink bottle effect, and the relative information is you can trust. Well, we have with the tomography, there's not a lot of techniques that actually overlap and give you the same information. So nitrogen adsorption produces a pore size distribution as well, but it's typically a different range from the MIP, much smaller pores. SEM is only visual, so you've got softwares you can use to do image analysis and work out pore size distribution, but it's superficial information, not 3D. So again, difficult to totally trust. The tomography is the one we've used. And the tomography is not, so if you want to use tomography to measure pore size, good luck, because they're really small, and the contrast between the clay and the air is typically not enough, not great, not enough to see something. That's why we actually use very small specimen, intruded them with mercury first and scan that, because we thought the mercury will be really, really visible. And in fact, it is. But then you've got the issue of you're basically measuring mercury after having performed the test. And if you look at the photo here, you see a lot of beads. And those beads are basically, when the mercury has been removed, it falls back, forms a bead in a pore. So that's probably in a pore bigger than the bead, and it won't give us exactly the shape of the pore here. So it's quite difficult to have different techniques, or we haven't found a solution. Maybe there is one, maybe somebody has done it, but we couldn't quite do it.